Okay, it's working. Okay, well, first, thank you for the invitation. It's a pleasure. I come from a university, and kind of a new university. It's in Saudi Arabia. It was in use 3 years ago. Now, for us, it's been a while around. So I will talk today on a prediction problem, a simulation exercise in the Gulf of Mexico. So it's about the ocean. A few years back, actually, British Petroleum came to us as they wanted to build a prediction system for the Gulf of Mexico. They have oil operations in the region. So back then, we had a meeting with Bruce Cornell, my boss at Scripps when I was there, and we had to argue between implementing 4D VAR or Yankee-F, as for everyone, I think, has to go through this problem. And after arguing, we decided that, okay, let's go with both and see what we get. So I will show you some results from what we get. And unfortunately, after we saw the results, we're arguing even more now. And then with the remaining time, I will talk about, hybrid is becoming quite popular somehow in the weather operational centers. And I will talk about another idea, alternative idea we're exploring. We're calling adaptive Yankee-F, very close to a hybrid. A simple idea, but it seems to work very well with small models. So I will talk about that. And I will finish just with some advertising of the things we're doing now in the Red Sea and the Saudi seas. I realize that I'm the last person standing between you and the lunch, so I'll try to do it as fast as I can. And I will use a lot from the previous talks. I will go as fast as I can. And actually, if I knew that what's going to happen in the previous talk, what's going to be presented in the previous talk, I would remove 15 or 20 slides of my talk. Okay, so it's about predicting the ocean circulation and how we predict the ocean circulation. I was working once in our campus, and I saw this announcement: how to predict the future is to invent it. It comes from a computer scientist. This is not how we do it in the ocean. The way we do it in the ocean, this is for advertising. Also, these are numerical models we're running in the Red Sea. And actually, we have now enough computing. We have good models that we can really integrate. They are very good in terms of numerics. And these are 1.5 kilometers in the Red Sea. It shows you the intrusion of the water from the Indian Ocean to the Red Sea. This is a wave model run by Sabek. He used to be here, and I stole him from here. Wave models. This is chlorophyll. This is chlorophyll. You see the chlorophyll, how the chlorophyll is getting transported. I missed it at the beginning by the eddies. So this is an ecosystem model, and this is 500-kilometer resolution model, 500 meters resolution model in the Persian Gulf. So, we have models. We know how to run them now. And the issue with models, as you all know, and you know more than me, probably, better than me, these are models that we get from discretizing the PDEs. The numerics are quite good. The issue is they are highly complex, very expensive, strongly linear, just name it. And they are chaotic, but even with that, we can, simulate. We can discretize them, put them on a supercomputer, and run them. The main issue with these models comes from the uncertainties. They have a lot of sources of uncertainties, from omitted physics, poorly known parameters, and certain inputs. The main one, I would say, and numerical errors are a small error. So at the end, when we run these models, we get some things that look like the truth, but it's not the truth. Combine all of these, we call it model error, obviously. So just quickly, what this represents, you have the data, assuming you have a very good initial condition. This is the truth. And when we run the model, we have an initial condition that is a little bit far, and we get something that looks like it. But it's not. So what do? We do what we just saw. We do a simulation. And so what we do is we combine models and data. And data, mainly the data guides the model where to go, and the model will interpolate the data over the whole grid because the data are sparse. And the goal is to predict, analyze, and quantify uncertainties of the ocean state. And the difficulties I just talked about, we deal with huge dimensions. We deal with everything, multi-physics, multi-variables, multi-state, multi-scales. And they are very expensive. One run is really expensive. And another problem that we don't talk enough about, mention enough, is that the statistical properties of the uncertainties in the system, we don't know them. And this is very important because if we want to quantify the uncertainties correctly, we need to know what are the uncertainties in the input. So how we formulate the data assimilation problem, 99% I would say of the assimilation methods are based on the Bayesian formulation. We tried lately to look at what they call the electrical engineering people robust filtering, robust formulation, but somehow we came back to the Bayesian. So the idea of Bayesian is to cast everything as stochastic, so you have a model that allows you to propagate the state in time from k minus 1 to k plus some stochastic term, and you have an observation system that observes the state with some stochastic term as well. And since the solution is stochastic, to determine the solution, you have to determine the probability distribution function of the solution. Once you have the probability distribution function, you can determine any statistics from this distribution. Okay, so this is so we want to estimate the state of the problem x0, x1 at any time given all the observation. So assuming you have the observation over one interval, you have all these observation, and you have a prior. Prior is an estimate of the first guess, if you want. So I put all the information. I want to estimate the state given all the information I have. With some probability formulas, Bayes rule, we can decompose this term into 3 terms showing up the likelihood, the prior, and the transition. This is the probability of the state given the previous state. If you assume everything is Gaussian, you will end up with this cost function that we minimize, and this is the Ford-Dirac cost function, if you want. This is the prior. This is model minus data, the misfit between model and data over the observation assimilation period. And this term comes from the fact that you're assuming that your model is not perfect. Now, if you assume that your model is perfect and you remove this term would disappear. And you come down to the standard Ford-Dirac equation, cost function, where you look for the initial condition that brings your model closer to the data and not far from your forecast or your background. And basically, I took the diagram I just showed before, and then now what we do is Ford-Dirac, this is my first guess. I look for the initial conditions that gets me closer to the data. Okay? So in the variational system, as you noticed, I took the data, all the data available over one interval. It's a dynamically consistent solution in the sense that it's a model solution. It respects the physics. So at the end of when I run my system, my estimate is a model solution. Okay? I didn't assume any model error in the system. And to implement it, it requires, as you know, an adjoint model and a non-convex optimization. Because if the model is linear, the function is non-convex, and you might very likely stuck in a local minima. But this will give you actually the mode, the maximum a posteriori solution of the Bayesian problem, if you have a very good optimization that can avoid local minima. And then what I will talk about forecast period is, once the data finishes, I'm running in a forecast mode. And where I have data, this is my assimilation period. Yes?
So you're saying that this is dynamically consistent, but so your adjoint model is linear, right?
Yes, but
you don't have any physics, so it is not a physical consistency.
But the solution is model output. The adjoint is only used to get the gradients to decrease, to reduce the cost function. But my solution is a model output. And a model output is dynamically consistent. It's the original model output. Okay, the gradients, forget about the adjoint. It's just a tool I use to optimize my cost function. If you have another tool, a stochastic optimization method you could use. And this, you have the full physics. But it's another story. So, the forward is for the solution, the backward is just for the gradients. Okay, so I can also use the Bayesian formulation.
The initial condition that you get, the minimum, could be, for example, out of balance.
True, but I'm talking about the forecast.
Yeah.
Just before I make the forecast. Correct. Okay, now I can formulate the problem sequentially, what we call filtering. And the goal here is to estimate the state given all the observations up to the estimation time. This is what we call filtering. It's designed for prediction mode. And then again, I can split it into 2 terms using Bayes, where I bring up 2 steps, 1 step for the analysis and 1 step for the forecast. Okay, so how we do it here, we start from, again, initial guess, initial conditions, then we run the model to make a forecast, And then this is what I call my prediction. So I'm updating a distribution. So I'm running the whole distribution with the model. And then when I get the data is far from the prediction. So what I do, I correct my prediction with the observation, and I get a new estimate that is close to the data. And then I get the analysis, and this is what we call analysis, and we can run again. So it's a prediction exercise. Every time I make a forecast with a model, I get the data, I correct my forecast, and I run again. And in here the data are assimilated sequentially. And so if we assume again that my statistics are Gaussian, then every time I do analysis is another optimization exercise where I'm looking for the state that is the closest to the data and not far from the forecast. The difference with the 4D var is here I had a sum where I was doing it over the whole window. If I'm assuming everything is Gaussian. Here, what shows up here is this background covariance that we just had.
About that stage,
I'm getting there. I will talk about this.
Okay.
I agree. I'm getting there. I will show 3 slides about it.
Okay.
I'm getting there. But say solution when the model is linear.
If you take the Hessian to be the estimate of the uncertainty,
Close enough. Locally. Yeah, but for I'm saying linear system. I will get to the uncertainties. And it's dynamically non-consistent. So when you talk to the variational people, the first thing he will tell you your solution is not dynamically consistent. I don't like it. And this is Bruce's argument, and we'll never get with that. Anyway, so what we need to know is that when the system is linear and the statistics are Gaussian, it's the same solution at the end of the assimilation window. When we don't have these constraints, these assumptions, then everything falls, and we don't know what we're getting. Okay, so how we used to do it, the sequential assimilation before. The sequential assimilation, we started from the analysis. I'm just depicting what I presented before. We run the model, we get a forecast, and when we get the data, we correct and we come back again. I'm saying good old days because this is optimal interpolation. And the good old days, the B was not updated. So basically, I'm running the model. I have a B that is somehow parameterized, and I use it to correct my forecast. In the new days, what we want is to update the probability distribution function directly. And to update the probability distribution function, we do it with Monte Carlo. You have the God of Monte Carlo here. You ask him, but we run an ensemble of models. And we run an ensemble of models. Assuming I start from a Gaussian, even if I'm starting from a Gaussian, I integrate it with a nonlinear model, I'll get a non-Gaussian distribution at the forecast. Okay, so the ensemble Kalman filter method, okay, we get a non-Gaussian distribution. I will discard that, and I will fit it to a Gaussian. I will take only the Gaussian part of the distribution. I'll throw everything than Gaussian. I will use that to correct my forecast. So it's again a best linear unbiased estimator in the eNKF. So basically, even if I'm propagating a non-Gaussian distribution in the model, at the analysis step, I'm assuming a Gaussian distribution, and I come back again. Okay, but the nice thing about this is that since you're updating distributions approximately, you're getting not only the estimate, but you're getting the uncertainties with the estimate. And this is a big thing. Good uncertainties, bad uncertainties is another story. Showcase very quickly, this is the Lorentz model that you atmospheric people know much better than me, but it's becoming a reference to test your assimilation schemes. I will show you just how this ensembles method works. What I'm plotting here is the eNKF with 20 members with the Lorentz. So here you see the 40 variables. Here you see the values of the variables. I'm starting from an initial guess. And on top of the initial guess, I'm putting 20 members. You don't see it. So the green is the truth, and in the blue are 20 members on top of the green. On top of the green, yes. And the error is like 10 to the minus 10. So an ensemble that is really, really close to the truth. I want to show you, even if you start from a very small error, after a few days, the error starts increasing. This is 6 hours, 1 day. I think around 2 days, you see the uncertainty starts propagating. And when you put the data, you reduce the uncertainties. This is a beautiful thing about this eNKF. It allows you to get an estimate of the uncertainty. Not the forecast error, an estimate of the forecast error. Okay. What's going on? Okay, so we took these and we implemented them with a real ocean problem. And so the problem is about estimating the front of the loop current in the Gulf of Mexico. So the current comes from here, turns around, it first the loop, they call it the loop current. and exit from Florida to form the Gulf Stream. So the oil companies are interested in the front of this loop current because they have a lot of oil operations in here. And if they are touched by this current, they cannot drill and they lose tons of money per day. So they wanted to predict the evolution of the loop current preferably 2 weeks in advance so they can adjust their operations and save a lot of money. So we used the MIT General Circulation Model, and we took all the data available in the region. There's not much. We have satellites, and
I can't tell the signs of your arrows. Is it a cyclonic or anticyclonic gyre, the loop current?
where? In here?
In the Gulf.
In here? It's coming from here and turning around. It's
So
going
it's
from
an
south, north.
anticyclonic
Anticyclonic,
gyre.
yeah.
Okay.
And Scripps also put gliders in the loop current to observe the loop current as well. So we wanted to use these to predict the loop current. And we worked with a lot of people, expert in the ENKF, Jeffrey Anderson, and with the Armin and Patrick from MIT with the adjoint. Okay, here's the MIT configuration. We have 10 kilometer resolution. The state is around 10 to the 7th. Forced by NSEP, initial conditions from HICOM. We nested the model with HICOM, the operational HICOM. And for predictions, we just use monthly climatology. So where I have data, I use NSEP and HICOM. Where not, I use monthly climatology. This is how the model looks before assimilation. It's not that bad. Yes, we implement that with Tim and Jeff, yes. And the idea was to use also satellites tracks, data from satellite tracks, to constrain the model with the data. Here I'm showing the satellite tracks over 6 months. Over 1 week, you only see 3 or 4 tracks. This is not what you get. This is 6 months of data. So over 1 week, you don't see much. Okay, so I implemented variation of 15 iterations, ENKFs with 50. We went further. I will not show these. They are still preliminary results. Yes. SST, gridded SST, it's here. And non-gridded satellite track, SSH. Everything is removed. Yes. It's not a good product. I will show you.
Do they give you the variance error associated?
No, just they give us the thing.
So how sparse are the data?
So as this is what I showed you. This is.
Sorry, too fast.
I'm sorry. Yeah, I'm trying. People want to have lunch. Okay, so these are the satellite tracks over 6 months. Over 1 week, you see 3, 4 tracks. Just 1, 2, 3, maybe like this. Depends on the week. That's a good question. This is what is assimilated every time. SST is gridded. SSH is not. Okay. Where I was. Okay, so 50 members, 15 iterations with the adjoint. Assimilation period 2 months and 2 months forecast. You have a glider data. I will not. I have results. I will not show it, but I can show you later on. I will use the glider data to validate the satellite assimilation, which is pretty. Actually, I was pretty surprised. I will show you. And the performance evaluation RMSE comparison with with what we were observing, but in the forecast period, and also comparison with HICOM and with the Aviso products, and with unassimilated gliders. Okay, so 2 months assimilation, 2 months forecast. Okay, I'm starting from here just to show you that the system is working quite well. This is what Aviso is giving. These are weekly forecasts from ENKF, from DART. And this is weekly analysis after putting the data, these satellites data. And this is the surface height. It looks really reasonable. The nice thing about it also, we have a higher resolution than what the data is giving. So this is only data product, Aviso product, that is only interpolating the data. Interpolating the data with the dynamics seems to provide a really nice.
How frequent are your
These are,
observations?
so here I'm putting them every week, here, but every week here. But later on I will put them every 3 days or even 1 day. But here it's only every week.
On the scale of the motions, that is quite
1 week, yes, I agree. Yeah, it's not ocean, it's ocean. It's a different time scale.
Very slow.
Yeah, it's very different word if you want. So I'm assignating 2 months. I'm running the adjoint over 2 months in the atmosphere.
Good luck.
Good luck. Okay, so now I show you that it's working well. This is 4D VAR comparison with the ENKF. Okay, This is this line here is splitting between the analysis period and the forecast period. I'm starting with 40 var. So black is, so 40 var is in the forecast. Forecast 40 var is just, I'm running the model. This is my forecast. I'm starting from place, I'm running the model. So it's a free run if you want. And the error is increasing over time. This is a HiCom solution. HiCom is a data assimilated solution. Okay, 1/12 degree global. And it's shown in orange. So, during the forecast, it's quite good because it's assimilated. It's not a forecast. This is what you need to know. So this is RMS, the errors. With the Aviso. Okay? The red one is the 4D var solution over the assimilation period and the 4D var solution over the forecast period. So it goes up at the beginning and then it gets not bad at all. For the eNKF, the same thing I'm plotting here. And so the eNKF is in red. It fits better than 4D var. The forecast is also better than 4D var up to here, up to 1 month. After 1 month, 4D var becomes better. And we try to understand why 4D var is becoming better later on. It fits better, eNKF. It gives you better forecast at the beginning. It doesn't give you, for some reason, it's not getting better. It's actually that's what we thought, but there is a reason for that. Okay, so here is the same figure, the figure at 1 month, after 1 month forecast. Okay, from eNKF, 4D var, HiCom, Aviso, and no, this was the forecast. This is the reference run without any assimilation, and this is HiCom. This is eNKF mean. What I'm calling by eNKF mean, when you get you run an ensemble filter, you get to a point in the forecast where you have an ensemble. Either you run the ensemble to make a forecast, or also, if you want to do it in the old days, I use the mean, and I make the forecast from the mean. Somehow, the shedding of in the loop current, it sheds an eddy, and it starts circulating in here. The shedding of the eddy is getting better somehow by just running the mean. I was a little bit disappointed by this result. Why? If I do the forecast, which is more expensive, and I integrate an ensemble, it's closer to the data, but the shedding in here is not that good. Somehow we're screwing the dynamics.
So your top things say exactly it says mean state on the left and...
Yeah, so eNKF mean is, what I meant is that I'm integrating it from the mean.
So you threw away the ensemble.
I'm showing the mean, exactly.
And kept the mean.
Yes, I'm just integrating the mean. So somehow
That's a better job of shedding.
yes, exactly, in the dynamics, But in terms of uncertainty, the other one, yes, exactly. And this is after 1 month. So this is what we noticed. Why? With 4D var, it really sheds it at exactly the right time. I will show you this later.
The fluid dynamics structure there, of course, is going to be a hyperbolic saddle when you shed the eddy. And what I'm wondering is keeping the mean suppresses some of the noise of the hyperbolic saddle and the pinching. That would be a guess.
It could be
actually having a whole bunch of ensemble members, let them go off the hyperbolic, on other directions.
I would really appreciate this and explain me this after the thing, but that would be great actually.
That's a guess.
It's a very good guess actually. I didn't know how to explain it.
So do any of the ensemble members actually do better in the pinching point? Because
I'm not showing the spread.
If you have a pinching point at different points, then it gets averaged in the mean. But each of the members, they get it right.
There is one,
They get it closer to
take only one.
Yeah, take only one.
I did one sample.
Yeah.
It could be. There are some of them that are close, yes, but maybe it depends on time as well.
Outliers might be having a big effect on the ensemble.
Yes, probably. This is the same figure, but for the forecast SST. Oh.
What's the MIT HiCom initial?
This is HiCom. This is MIT nested in HiCom.
That's your perfect model, right?
It's my free run model. Exactly. Yeah. Okay. Now here compared to the TMI, and you see the TMI data, the map TMI data, they are not that good actually.
That's not assimilated.
No, this is what TMI gives you products.
But it's not assimilated into...
No, not this.
Yeah.
Now here is interesting also. This is the eNKF mean, and there is eNKF the average of the forecast. So here the average of the forecast is really much better than just running the mean. Yeah. Here for DVAR, running with the SST for a long time, it seems that the ensemble is doing much better than running only integrating one. And again, I don't understand much why it works much better here with the SST. It works less. It's a dynamical.
So I'm just trying to straighten it out. The satellite is measuring sea surface height.
Yes.
And so this is a predicted variable.
Yes.
It's doing much worse.
No, I'm assimilating. So what I'm doing, I'm assimilating sea surface temperature and sea surface height in here. The period, and here is the forecast period where I'm not assimilating.
Okay, sorry.
So I'm assimilating both.
You're assimilating both.
Yes, yeah, I'm assimilating both.
Sorry.
No, my bad. I'm going fast. Sorry.
But where are you getting SST from? Because the satellite
These are
has height most.
no, the AVHRR for the assimilated one.
Oh, I see. Sorry. Forgot.
Okay, so now here we'll show you just a figure. It looks complicated, but it's not. It shows you actually where we're measuring when the shedding of the eddy happens. So this is the extent of the loop current in the west and in the north, and the length of the loop current. We measure it according to the 17 centimeters contours. And what's showing basically is in the red Aviso, this is what interpolating the data, it shows when the eddy is separating. And for DVAR, you see it. It's amazingly, it sheds it at really exactly the right time in the forecast. Somehow in the forecast, every 1 month, the shedding of the eddy for DVAR is getting it really correctly. And this is why, after 1 month, the forecast becomes better in for DVAR. While the eNKF is getting it not at the right time. So the shedding, the difference we're seeing in the loop current, the shedding is not happening at the right time. And we think this is because of the dynamically consistent solution. There are something in the dynamics that needs to be correct in order to get the right shedding in the loop current. And finally, from this, I will compare the two solutions to a data that we're not assimilating salinity with gliders in this area. So this is the salinity from glider. This is the salinity from assimilation, without assimilation. This is the assimilation with the MIT, with the 4DVAR. This is the difference with the glider from the eNKF. This is every day, okay? And this is a profile. And you see with assimilation, I was surprised actually to see that the assimilation improves that much in an area that is completely independent, and salinity that is completely independent in depth. And finally, this is a figure from eNKF showing propagation of uncertainties, propagation of the spread of the ensemble. I'm calling it propagation of uncertainty. After 1 week, 2 weeks, 3 weeks, and 4 weeks. And you see the uncertainties are getting concentrated over the shedding area, which is very interesting. Okay, but it gives you an information. You believe in the information or not, it's another story. But this is your best estimate of the forecast error, of the forecast uncertainties. This was in SSH.
No, it's actually forecast error, analysis uncertainty.
This is forecast uncertainties.
Forecast process error. Maybe to be clear.
And last movie to show you how we could use these uncertainties for a user. Because the users want to see how we could use these uncertainties. So what you will see, the mouse will propagate in here. And when you put the mouse on one point, you will see the distribution of the point. So it tells you how much you trust your uncertainties, your forecast. This is at the beginning of the assimilation window and at the end of the assimilation window, after 2 months, and you will see how the errors will decrease. So I will run this. Where is the mouse? Here. And you see when you put the mouse interactively, you see how much you trust. When you get to the loop current, the uncertainties are large. You can flip it. You can do whatever you want with it. Visualization people like this. And then after another cycle at the end, you see the distribution, it went much smaller, and even the distribution became more Gaussian, which is pretty cool. Okay, so to finish with these, To finish with this, everyone agrees that it's essential. We have the MIT GCM. The nice thing about it, we have these two systems implemented. We spent like 6-7 years putting these two systems, and they are available now, and we can run them without much difficulty. From the first experience, I already said it. It fits better the data, and it's better for short-term predictions, the eNKF, and it gives you uncertainties, estimate of uncertainties. For DVAR, it's dynamically consistent, and it looks like it's better on the long term. So I don't know. It's up to you to choose. And there's still room for improvements. I'm summarizing here the good thing about the 4DVAR and the good thing about the eNKF, which I'm just summary. So in orange, which I see is not very good, while in green, it's a good thing. It requires an adjoint model, so you have to build an adjoint model. And the MIT GCM, we put around 4 or 5 years to just put the adjoint. And every time you change the model, you have to make sure you change the adjoint. The eNKF is portable, so I went to Jeff. We worked 3 months with Tim Hoare, and then somehow it worked. It's full rank in the sense that the eNKF, it's a limited rank because you're running a limited ensemble. You cannot run a lot. So it's 4DVAR gives you a full rank, and it gives you the mode of the PDF. The eNKF is rank deficient. So here I didn't mention it, but we're implementing it with localization and inflation. I'll talk about it. No efficient method to propagate uncertainties, while here it gives you some estimates. It's a dynamically consistent solution. It's a dynamically non-consistent solution. Okay, so what people are trying to do is, okay, I have these two systems, and each one has some good features. Why we don't combine them? And this is what they are calling hybrid. And it's becoming very popular somehow. But when you look deeply, it's really empirical methods. So in the eNKF, the accurate description of the background is very important. And the limitation of the eNKF background is coming from 2 sources mainly. The ensemble is small, and uncertainties that are not accounting for. So small ensembles make a rank deficient, spurious correlations. So a data in one point will correct. So that's what we've been discussing in the previous talk. And the covariance is underestimated because we're not also accounting for all the uncertainties in the system. So what people are suggesting, so basically what's happening is that the eNKF background is an approximation of the truth. So if this is the truth, this is what you get from eNKF, covariance background. There's this part that is missing. Okay? So what people are doing inflation, where you just multiply the covariance, you inflate it basically by a factor. And they do localization, where you make the low rank covariance as a full rank just by cutting off the long-term correlations. And actually these, you can somehow see them as representing this matrix B that is missing. Hybrid that is becoming very popular is they said, okay, I have a B for variational that I worked a lot on it, that is full rank, and I have the P from the eNKF that is low rank. I'm just add them up. It's really empirical. I don't know how it works. But they just add them up, and you can see it as kind of also as kind of inflation, but inflation for the whole covariance, not as part. And this is what they call hybrid eNKF for DVAR. And you can also mix all these eventually. Okay, we're looking at the problem in a different way. So what we're trying to see is we're acknowledging that there is a null space in the ensemble. And the question how we could sample some, we can generate some samples from the null space of the ensemble. So how to see this null space is basically the only way to see it is from the analysis error, what I'm calling residuals. So if the background is not good, this will be reflected in your fitted solution. So the idea is the residuals, this analysis error, will get information about what's missing in the background. So the idea is to generate some members from the analysis, from the null space, and try to put it as a new ensemble member. It's a different way of looking at things. So basically, this is a state space, okay, and X, and this is the truth. And the ensemble space is the subspace of the state space. And there is this mismatch between the truth and the estimate. If you project this into the observation space where you have the information, the only place where you have information, It's the same thing in the observation space, and this delta x projected by the observation operator will be manifested as a residual. The idea is we want to use this R to estimate this mismatch and put it as a new member. So it's kind of generating new members from the null space. Very easily, it's not...
How do you replace the old members?
I'm getting there. You're always faster. But yes, that's where the cooking starts.
Yes.
I'm getting there. So, very easily you can show that it's just an inverse problem, where, you have R and you want to estimate delta X in the observation, from the observation space in the full space. Okay, and you write it as an OI problem, and one new member we generated this way. We just add delta X as a new member in the ensemble. We have another version of it where we use the adjoint. So you have the residual, you integrate it backward in the adjoint, so to include more information in the process. You integrate it backward, and then you integrate it forward to get a new member. So this new member has more information from all the residuals and dynamically more consistent. Otherwise, the rest is the same. But the idea is to integrate it backward with the adjoint with a 4D-var formulation instead of inverse time invariant estimate. Okay, so here we come to Andy's. The problem is that when you put new members, you're increasing your ensemble. And after a while, your ensemble becomes very big. You have to drop some. So this is the cooking I'm talking about, is we had to drop some. And the one we dropped is the one that contributes the least to the spread. So the idea is we want to drop the ones that distort the distribution the least. I'm not putting all the equations here, but this is the idea. I'm removing new, and I'm putting a new one. And actually, you can not only estimate one. If you assume that your null space, your estimate has a Gaussian distribution, you can sample more. Not one, you can sample dozens and put them as a new members as long as you can handle them. So adaptive versus hybrid, and adaptive is because every time you put a new member from the residuals. So the adaptive idea is to limit the growth of the ensemble to the directions indicated by the residuals. In the hybrid, you're just adding a matrix. In the adaptive, you're just selecting some members from this according to the residual errors. So you're selecting some direction. And it's easy to implement because the two systems are implemented completely separately. I have a residual error, I estimate, I put it in, and I'm done. The issue with it is, technically speaking, you're adding a new member, but you're not changing the rank. So you still have the rank deficiency problem, and you have to do it with localization. Okay, just to finish, experiment again with Lawrence 96, and we tried it with all variables, half, and quarter variables. We have included a model error where the forcing, instead of 8, we're using it as 6. Sampling errors, we included also model errors and sampling errors. We use 10 members. And what I will show you here are results with different inflation, different localization. And here is the RMS from the ENKF, from the hybrid, from the 3D variant of this adaptive thing. And what you could see that in all cases, the hybrid really works surprisingly well, somehow. And the ENKF even improves over hybrid. The other...
Your hybrid, how did you choose your coefficient?
So we ran a lot, and at the end, the best one we found, it was, if I remember correctly, 0.8 or 0.9.
It's basically just a covariance inflation.
It is a covariance inflation, exactly.
Using a background covariance.
Yeah, but with some dynamics. Yeah, that's what I said.
Whereas this one is probably adaptively inflated.
Exactly. Yeah, from the residuals. This is how we're explaining it. So here another comparison where we used a bad B, and we just put identity. So here it becomes just an inflation, if you want. Compared to the ENKF, and here's the purpose of this slide was to show that propagating the residual backwards and forward, if your B is not good enough, it will help you. And this is exactly what we're saying, that when the B is not good, what you're adding has no good dynamics in it, propagating the ensemble, the new member backward and forward, would bring some dynamics to the problem. And this is exactly what we're seeing. The same figure, just also with the adjoint, showing that how many steps you integrate your, yes, I need 3. how many steps you integrate your residual backward in time. 4 steps, 3 steps, 2 steps, 1 step. Just the backward integration of the new member. And it shows that the more you integrate, the better it is. But you can integrate up to a certain limit because of the adjoint stability issue. So here we could only come back to 4 steps. So to finish, also empirical, really empirical, combining these two might give you something. I was skeptical at the beginning. What I'm seeing is they look good enough. They improve a lot, somehow. This, however, requires implementing the 2 systems. And it's not easy problem thing. Somehow, as I said, when you go to weather centers, ECMWF, you will only hear hybrid. Maybe politically it's a good thing, because the ensemble people and the Vardivar people are both happy. They both have jobs. Hybrid uses the ENCAF to improve the background. What we're using the variational to enrich the ENCAF. It's close to each other. These are some references. I think we don't have time. Just to advertise, this is, lately we got a project with Aramco. They want to drill in the Red Sea. And they want operational system for the whole Red Sea on everything. So the project, the center, if you want to, will start in April 1st. And we're putting all this capability. So far we have the atmosphere, the ecology, the circulation, the waves, and the oil spill, each separately running. We're working on the assimilation for each. And on the long term, it's a 10 years project, is to couple these also. It looks like science fiction, but this is what they want. And just to show you, this is an ENCAF assimilation system at 10 kilometers in the Saudi Sea area. This is India here. But we could easily also extend it to include the whole Indian Ocean, if there is interest in here. We only have 2 cycles assimilation now. But we put 1.5 years to import from the cluster, this MIT DART, to a Blue Gene. Dealing with Blue Gene, I would never do it again. It's running now, but it's not running fully. What's going on is that what we were doing is making it fully parallel. We have 70,000 CPUs. I wanted to use all of them. So the idea was to run 1,000 members at the same time. What we found out after putting this system is that the Blue Gene doesn't allow you to run them all at the same time. They all have to go to the queue. And then I looked at the guy. I told him, now you're telling me? After 1.5 years, I'm trying to import the system, and now I have to go to the queue. So if one is stuck, the whole system is stuck. What I liked about adaptive in here is that what we could envision is that if few are stuck, after a while, drop them, get a new one, and then continue, for practical reasons. These are the people I'm working on, the ocean people and our collaborators, many of them. It's not, without them, it's going to be very hard. And just to finish, particles that we seed on time in the Red Sea, and you see them how to propagate, so you can move this interactively, put it here, put particles, and see start circulate, and these are streamlines also the same way. We can seed them as we go for the users in the, we have a very cool screen on Aramco. When they come, they like them. So we show them these, we don't show them the equations. Okay, thank you very much. Yes?
So the most common systems struggle. The most of applied ensemble Kalman system struggle from they need initialization. So, or they are far from what the...
It's a dynamic consistency.
Yes.
Where we're seeing in the loop current. It seems that we have to get this. I don't know exactly what's causing the shedding.
So my question is, in the atmosphere, in the ensemble Kalman filter systems for the atmosphere, they try to measure this departure from the balanced or model state by, for example, surface pressure tendency. What would be corresponding parameter and measure for the ocean model? How can you...
Geostrophic balance in the ocean somehow should be make sure that it's respected.
So how can you measure in your model why your ensemble system is not doing so good job compared to Fodivar?
I have to understand.
How can you measure this problem?
I have to understand what's causing the shedding of the eddy first in the Gulf of Mexico to be able to explain why I'm not getting it in the ensemble. We still, up to now, the physical oceanograph do not understand what's causing this separation. They don't know what's causing the separation. Some of them, they say it's some instability coming from an area near the, where is that? Near the South America and propagating and causing this shedding, some of them, they say, no, it's in the initial conditions. I don't know. But this could be one possibility that, I would love to hear about it.
Probably one explanation.
Yeah, for now, I don't have any explanation. We just reported.
So I find this a paradox. I mean, the ensemble filters are actually predicting much better than 4D VAR until the eddy sheds.
Yes.
And to me, it looks like an accident 4D VAR did so well.
I don't know. According to Bruce, this is his main selling point. He wanted to see that 4D VAR is doing something good, and when he saw that, he jumped. Look, I told you.
And can you say how? So the shedding was off by how much by the ensemble filter?
A few days, if you want. Few days.
2 days.
Few days.
Few days.
Let me see. You can see it.
No, that's okay. Just
okay.
I take your word.
Few days. Few days. Now, something I didn't show, something that is also not explored much yet. Here I showed you with 50 members and 15 iterations, and this makes them both at the same computational time. In the eNKF, I can run 200 or 300, and I will improve the results. In the 4D VAR, if I do more iterations, it's not improving. These need to be analyzed. And if with new members, I might get a better distribution forecast, it might improve. So this need to be seen more in depth. But I'm showing 15 and 50. But what we notice is that the more you add members, the better you still see the eNKF improving. While after more iterations, the eNKF, the 4D VAR is fitting noise, basically. And it's not improving at all. It might sometimes make it even worse.
But then how would you explain physically? What is that what 4D VAR is adding in the hybrid approach?
In the hybrid?
Yeah, what is
In the hybrid, I didn't try it.
I think this is you're arguing between chicken and egg because 4D VAR has its own caveat, like all the background covariance is specified one way, and then ensemble filter has like ensemble
statistics
and this and that, so it's really hard. It is an ambiguous setting. You cannot even compare anything, in my opinion.
The 4D VAR.
But you have to understand what is the physical value of the edited information.
It's not that easy.
To discuss this on the line.
Yeah. Thank you very much.